This is the notes recording for chapter 27. So let's begin by comparing digestion and metabolism. With digestion, we see mechanisms, three main mechanisms like absorption, secretion, and of course, the act of breaking down food. And we need secretions to break down food. And then, of course, we absorb them. How are these related to metabolism? Well, digestion is going to fuel your resource needs so that you can carry out metabolic processes. And the two main metabolic processes are catabolism which is the act of breaking things down, and a good example in the body is cellular respiration. And then the other one is anabolism, which is making stuff or building stuff. An example of this would be building muscle. Now let's take a look at the fluid volume that we gain from these digestive mechanisms. With ingestion, we gain about 2 liters. So that means that we ingest about 2 liters of volume of food or fluids. With secretion, we gain about 1.5 liters from our salivary glands. We gain about 0.5 liters from our gallbladder, 2 liters from our stomach, 1.5 liters from the pancreas, and about 1.5 liters from the intestines. And if we add all of this up, that totals at around 7 liters total volume. So now if we absorb some of this, it will happen in the small intestine and in the large intestine. The small intestine, we absorb about 7.5 liters. In the large intestine, we absorb about 1.4 liters. So what does all of this mean? So between ingestion and secretion, we get a total of about 9 liters. And then we absorb 8.9 of this. So that means we only excrete 0.1 liters in the form of feces. That's not very much when we think about it. In reality, we probably ingest more of this, more than 2 liters. So that means in America, we're more than likely overeating. Okay, so let's look at our 3 nutrient biomolecules. These 3 biomolecules are carbs, carbohydrates, proteins, and lipids. And to digest these, we need enzymes to gain nutrients from them. Carbohydrates, the enzymes that are first added in, come in the mouth, and that's with salivary amylase. Salivary amylase. And salivary amylase will begin to digest starch. And if you remember, starch is actually a long chain of carbohydrates or a long chain of glucose. So it's like, here's a glucose connected to another glucose, connected to another glucose, and so forth. So it's a long group of glucose molecules. We also see carbohydrate digestion in the small intestine. We use enzymes like maltase to digest maltose. and it will break maltose down into a glucose and a glucose molecule. Another enzyme would be lactase, which will break down the dietary sugar lactose into a galactose and a glucose molecule. So then the other one would be sucrase, which breaks down sucrose into a fructose and a glucose molecule. So these here in yellow are disaccharides, so two monosaccharides bonded together, and these enzymes here in the small intestine, maltase, lactase, this is supposed to be an S, and sucrase break down these disaccharides, maltose, lactose, and sucrose, into monosaccharides like glucose molecules or galactose molecule or fructose molecule. So make sure that you know these. So what about protein digestion? Well, it begins in the stomach with the help of pepsinogen. And pepsinogen ends in ogen, so we know it is a zymogen. And a zymogen is an inactive enzyme. Pepsinogen, since it is inactive, will need something else to make it become active. And it just so happens the stomach secretes hydrochloric acid, which activates pepsinogen into the active form pepsin, which will help digest proteins. We also see protein digestion in the small intestine. Enzymes, pancreatic enzymes secreted in the small intestine, and brush border enzymes will help digest proteins into smaller proteins that are 1 to 2 amino acid chains long. So remember, proteins are polymers of amino acids. So a protein would look something like this, an amino acid bonded to another one, and another one. And the enzymes in the small intestine would come in and break apart these bonds between the amino acids, called peptide bonds, into smaller chains of amino acids. And then finally, lipids. Where do we see lipid digestion? Well, it happens in the small intestine with the aid of an enzyme called a lipase, which are the fat digesters. Remember, bile comes in from the gallbladder, and it helps to emulsify fat. And really what that does is it increases the surface area on fats that's available for these lipases to come in and break apart the fat molecules. Now that we've talked about the digestion of these molecules, let's talk about how they are absorbed in the walls of the intestine. So here we have a small intestinal cell, and we can see that we have some microvilli, which increases the surface area, increases the ability of absorption, and we're going to have some transporters that aid in absorption of molecules. So some important ones here are going to be a glut transporter, which is a glucose transporter. Sorry, this first one is actually a sigil. Which is a sodium glucose transporter. And another one is going to be a glut transporter, which is a glucose transporter. Okay. So when we have carbohydrates that have been digested into small, like monosaccharide carbohydrates, such as glucose, they are ready to be absorbed by the walls of the intestine. And we're going to use a SIGALT transporter to do this first. What happens is it uses sodium to move down its concentration gradient, because sodium is found in high concentrations here in the lumen of the intestine and in lower concentrations inside of the cell. So it moves down its concentration gradient, and when it does this, it pulls glucose in with it. So now we have glucose inside of the cell. But we also have sodium. We don't want sodium to stay here. So we're going to use another transporter that are found on nearly every single cell in your body, and that's a sodium-potassium pump. So this is a sodium-potassium pump. And what it does is it uses, of course, ATP to ship sodium out and potassium found out here in. So we do have some potassium inside the cell now, but typically there are potassium channels found in the cell that will ship potassium back out, so that we keep our resting membrane potential of the cell the same. Alright, so what was the main purpose of this cell right now? What were we trying to do? And that was to get glucose absorbed where? Into the bloodstream. So we want glucose in the bloodstream. But right now, glucose is in the cell. So we want to get it here in the bloodstream. And what does this is the glut transporter, here in pink. It takes the glucose that is in the cell and it moves it down its concentration gradient. Because glucose now is in higher concentrations inside of the cell than outside of the cell, allowing it to move down its concentration gradient. And now we have glucose in the blood, which is what we wanted to do in the first place. So that is glucose or carbohydrate absorption. So why doesn't a small intestinal cell hold on to the glucose and use it for itself? It's because these intestinal cells can't actually eat or utilize glucose. They only eat or utilize what's called glutamine. Okay, and which is a good thing, or else we would never be able to absorb glucose into the blood. It would just all stay in the cell and they would use it for themselves. Okay. So carbohydrates. Carbohydrates found mainly in plants are our number one fuel source. Means we're going to use carbohydrates first for fuel. And the one most often talked about is glucose, which is a monosaccharide. Here's what its chemical structure looks like. You do need to know its chemical formula, which is C6H12O6. For all carbohydrates, it is a 1 to 2 to 1 ratio. And we see here that it matches, glucose matches. So for every one carbohydrate, for every one carbon, we have 2 hydrogens and then 1 oxygen. And all carbohydrates will follow this ratio. So what types of carbohydrates are there? Well, we have sugars, like monosaccharides, which is glucose, disaccharides, and so forth, or polysaccharides. An example of a polysaccharide would then be starch, which remember is a long group or long chain of glucose molecules. And then there's another one called, this group is called fibers. An example of this would be cellulose. And these chains are extremely long. So the numbers here, so see with glucose how these are small, 6, 12, and 6. These numbers would be in the thousands. So they would be extremely hard to digest into monosaccharides so that we could absorb them, which is why in general we cannot utilize cellulose or digest cellulose in our diet. Okay. Short-term storage of carbohydrates are in the liver and in the muscles in the form of glycogen. And if you eat too much carbohydrates, it gets converted into fats and stored as adipose. Okay, I'm going to come back to proteins. Let's do protein absorption first. Okay, so what happens with protein absorption? Well, we know that proteins are polymers of amino acids held together by bonds called peptide bonds. Okay. Well, since our body uses over 20 amino acids, or we use 20 different amino acids to form all these proteins, we're going to have many different transporters that we use to absorb these proteins. So I'm just going to use a general one here. So this is just a general amino acid transporter. Okay. There are many different kinds. This one will use sodium to move down its concentration gradient, and the amino acid will then come in and hitch a ride. Since we now have sodium inside of the cell, the small intestinal cell, we'll need a sodium-potassium pump to reestablish membrane potential, resting membrane potential. In doing so, we can get sodium back out, but remember, potassium comes in, so we'll need a potassium channel to push that potassium out again. On the other side, on the basal side of the cell, remember this would be the luminal edge, we'll have another amino acid transporter that will basically do the same thing. It'll use sodium to move down its concentration gradient, and then in doing so, the amino acid will move out and can be absorbed into the blood. Really what I want you to take from this is that since we utilize 20 different amino acids to make all the proteins in our body, we will have many different types of amino acid transporters that we use to absorb proteins. Okay. So proteins. Proteins are not our number 2 source of fuel, but our number 3. Remember, proteins make up our muscles, and we don't want to use our muscles up before we use our fats, right? So that means fats is going to be our number 2 fuel source. Where do we get proteins from? Most of them, of course, come from animal products, but they really can be found anywhere. What are they used for? Well, like we said, let me back up a bit. They're synthesized from 20 different amino acids, and they can be used for things like enzymes, hormones, and even to transport oxygen in the body. Okay. Of these 20 amino acids, 8 are essential, meaning we have to consume them in our diet. That means 12 of them are synthesized in our body somehow. Okay, so 8 of them are essential, meaning we have to take them in our diet, but 12 of them are synthesized in our body. If something is a complete protein, that means it contains all 8 essential amino acids. But if it's incomplete, it's missing one or more. Of the 8. Okay, so make sure that you know these definitions and know that we have 8 essential and 12 are synthesized by our body. What about lipids? Well, we said lipids are actually our number 2 fuel source. So we'll use our carbohydrates up, and then we go to our lipids or our fats, and then we go to our proteins. Well, there are different types of lipids. We have triglycerides, we have cholesterol, and then what are called lipoproteins. So triglycerides are probably what you hear of the most. Triglycerides, we have a glycerol head, and then 3 fatty acid chains. We have different types of triglycerides. We have saturated triglycerides, which have no double bonds in their fatty acid chains, which are then solid at room temperature. So those are like butter or lard. And then we have unsaturated, which have one double bond and are liquid at room temperature. You can have poly unsaturated. There should be a UN right there, which have 2 or more double bonds and are also liquid at room temperature. Okay, so cholesterol. So cholesterol always has a bad rap, but cholesterol is needed in the human body. It's actually a precursor for some hormones, steroid hormones like testosterone and estrogen, and is also used in the plasma membrane of cells. The more cholesterol that is found in the plasma membrane, the more waterproof it is, because remember, lipids are what's called hydrophobic, meaning they repel water. And then finally, we have lipoproteins, which are lipids wrapped up with proteins. And some examples of these are LDLs, low-density lipids, HDLs, which are high-density lipids, and then one you've heard of before, chylomicrons. These are actually lipoproteins, lipids wrapped up in proteins. So we're going to look at what these are real quick. So you've probably heard of these before. These are what you check whenever you go to the doctor. They will also check these whenever they check your triglycerides and your cholesterol. And I want you to guess which ones of these you think is the good lipoprotein based on percentages. So with a low density lipid, this would be the percentage, roughly the percentage of lipid compared to protein. This is the protein, this is the lipid. With HDLs, this would be an example of the lipid versus the percentage of protein. So based on this, what would be your initial thought of what would be a better lipoprotein? The high density lipid or the low density lipid? Hopefully you guessed the high density lipid. This would be the good lipoprotein. You want more HDLs. They help to strengthen the walls of your vessels. The more LDLs you have, the more likely you are to develop plaque and atherosclerosis in your vessels, which is of course not good and leads to cardiovascular disease. What about lipid absorption? How does that happen? Well, here we have a fat molecule and a villus in the walls of the intestine. And actually on the villus, the cells themselves then have microvilli. And all of this aims to increase surface area to increase absorption. So as the enzymes come in, they will break down this fat molecule into smaller pieces, into fatty acids and glycerol. And as the fatty acids enter the cell, it will be processed by the smooth endoplasmic reticulum. Then it's shipped to the Golgi and packaged. And then from there, it's exocytosed out. But where does it go from there? If you remember, once it's here, it is also a hydrophobic molecule. So it ends up becoming things like a chylomicron. And they're just too big to be absorbed into the blood. So we have to take a different pathway. And the reason I drew it like this is because I want to show you that often the lymphatic capillaries jut up into the villi of the smooth intestine. And of course, it's surrounded by nets of capillaries. But since these chylomicrons now are too big to be absorbed into the blood, they have to take the pathway of least resistance, and that is into the lymphatic capillary. And if you remember, they have a special name whenever they're in the small intestine. They're called lacteals. So make sure that you know that name. Okay. Also, the enzyme that helps to break down the fat molecule, remember, are called lipases. So bile comes in and emulsifies it, and then the enzymes come in and cut it up into fatty acids and glycerol. The fatty acids then are taken into the cell and exocytosed and then taken up by the lymphatic capillaries called lacteals. Okay, now let's go over some vitamins. Vitamins are termed organic, meaning they contain carbon. And they're found in all major food groups, but only in small amounts. And if they are essential vitamins, that means we must obtain them in our diet somehow. If they are non-essential, that means we synthesize them in our body. So the essential vitamins are broken down into two groups, either lipid soluble, meaning they dissolve in fat, or water soluble, meaning they dissolve in water. The lipid solubles are vitamin D, E, K, and A. Vitamin D is used for the absorption of calcium from the GI tract. Vitamin E helps to protect cell membranes. Vitamin K is needed for making blood clotting proteins. And vitamin A is actually a precursor for a visual pigment. So it's a precursor for a visual pigment. You may have heard that vitamin A is found in things like carrots, carotene. So precursor for a visual pigment. So it's good for your eyes. The water-soluble vitamins are the B vitamins and then vitamin C. There are many different B vitamins, so I'm going to have to draw these out to the side. Most of them are involved in either metabolism or some sort of nutrition oxidation. So vitamin B1 or thiamine is used for carbohydrate metabolism. Vitamin B2, 3, 5, and 7. So 2, 3, 5, and 7 are actually all used for nutrient oxidation. Which is, of course, a chemical reaction. That leaves 6, 9, and 12. So B6 is used for protein metabolism. B9, which is folic acid, is used for red blood cell formation. And it actually helps to prevent pregnant women. It's in their prenatal vitamins, and they need enough B9 or folic acid so that whenever their baby is developing in the womb, they don't develop what's called spina bifida. Spina bifida. B12 is also used for red blood cell formation and nerve cell maintenance. So it helps maintain nerve cells. Okay. And then vitamin C, which is an antioxidant. And actually helps with collagen formation. Collagen is the most abundant protein in your body. These last two, these non-essential vitamins, meaning we can form them in our body, are also called cofactors. We'll see these later when we talk about cellular respiration. The first one is NADH. The next one is FADH2. I'll refer to these as electron carriers. They occur in cellular respiration and can actually be cash-gen for ATP. So we term them as cofactors, but there are high energy molecules. Now minerals. Minerals are inorganic, meaning they do not contain carbon. If they are major minerals, that means we require more than 100 milligrams a day. If they are trace, we require less than 100 milligrams a day. There are 7 major minerals, which I will ask you to know: calcium, chlorine, magnesium, phosphorus, potassium, sodium, and sulfur. I'm not going to go over what each of these do. They're in the notes that go along with this video. From your trace minerals, there are many different trace minerals, but these are the 5 that I'm going to ask you to know. From these, zinc is used in immunity and wound healing. And then iron is, of course, a component of hemoglobin. So now we can't talk about nutrition or nutrients and metabolism without going over glucose homeostasis. So let's get some of these sugar effects out of the way. Glucose is needed by the brain. There's no getting around this. The brain can only metabolize glucose. At fasting, which means no food for around 2 hours, your blood glucose levels should be about 80 to 90 milligrams per deciliter of blood. Then, after a meal, after you've eaten a meal, your blood glucose should be around 120 to 140, depending on what you eat, milligrams per deciliter of blood. So then, after 2 hours, what should your blood glucose be? In a normal, healthy individual, your blood glucose should return after 2 hours back to 80 to 90 milligrams per deciliter. Prolonged blood glucose levels of 120 milligrams per deciliter or even greater is called hyperglycemia. This causes an increase in the concentration in the blood. It causes an increase in the osmotic pressure. That can lead to increase in urination and then dehydration. Increased levels of glucose in the vessels can damage the endothelium lining the vessels, and this will then lead to things like cardiovascular disease. And glucose actually acts as an inflammatory agent, which then, of course, damages the walls of the vessel. On the flip side, if you have prolonged levels that are less than 70 milligrams per deciliter, we call that hypoglycemia. If they are less than 50 milligrams per deciliter for periods of time, we call this hypoglycemic shock. This can lead to a range of things like irritability, to seizures, and even coma and possibly death. Now it's important that we understand what happens to glucose in the blood. Okay. And it wouldn't really do anything if it wasn't for this hormone called insulin. Insulin comes from the pancreas. The pancreas is an exocrine and an endocrine organ. 99% of it is exocrine. That means it's dumped into the digestive tract. Only 1% is endocrine, meaning it's forming these hormones dumped into the blood. And they come from sections in the pancreas called islets of Langerhans. One of these cells are called beta cells, and the beta cells are the ones that make insulin. Beta cells make insulin. So this is going to be our beta cell. So in this scenario, we have a high concentration of glucose in the blood, meaning we probably just ate something really sugary. So this is not fasting, this is right after a meal. So how are we going to get this glucose out? Well, first we need insulin secretion, and that's going to come from our beta cells in the islets of Langerhans in the pancreas. So we're going to need some transporters. You're going to see a glut transporter. If you remember, that's a glucose transporter. We're going to see a potassium channel. We're going to see a calcium channel. And these beta cells contain vesicles that are actually holding insulin, the hormone insulin. So let's see what happens here. So like all cells, they have mitochondria in them. And they're going to play a role too. So that's a mitochondria. Now we've set the scene. So we have high concentrations of glucose in the blood. And when we have high concentrations, it can move down its concentration gradient through a glut transporter into the cell. Now this glucose is going to be utilized by the mitochondria through cellular respiration to make energy in the form of ATP. And as concentrations of ATP increase, that's going to change our leaky potassium channels here. Okay, so right now they're leaking potassium. And as concentrations of ATP rise, they will shut off this channel. They close this potassium channel. That's going to change the membrane potential of this beta cell. It makes it more positive because potassium, it has a positive charge. So as potassium builds up in the cell, we get more potassium in the cell, the membrane potential of the cell becomes more positive. And it just so happens that this calcium channel is a voltage-gated calcium channel. And as this voltage rises, it opens the calcium channel and allows calcium to come in. So now we have calcium inside of our cell. So you remember these vesicles holding insulin inside of our beta cell? Well, they have binding sites that are specific for calcium now. Okay, so how did we get a buildup of calcium in the cell? Our membrane potential changed due to the buildup of ATP that opened the voltage-gated calcium channel. Now we have calcium in the cell. It binded to the vesicle, the insulin vesicle, and that's going to cause an exocytosis of insulin. And now we have insulin in the blood, and that's insulin secretion. Okay? So the point of all of this was just to get insulin into the blood. So this is insulin secretion. Now let's see how insulin in the blood acts to get glucose into the cells. So what is insulin's mechanism? So you have two types of cells. You have insulin-dependent cells and then non-dependent cells. We're going to use the example of the liver Most cells are insulin dependent, but some are not, like the brain, but we're going to use the liver cell as an example. So let's do an insulin dependent cell first. So what's the scenario look like in our blood? Well, we know we have glucose hanging out in the blood. And we just secreted a bunch of insulin, so we also have insulin in the blood. And insulin is a hormone, so we're going to need a receptor for this hormone. So this is going to be our insulin receptor. It's an insulin receptor. So when we have glucose and insulin in the blood, this hormone will bind to its insulin receptor. This causes a second messenger cascade. Second messenger cascade. And in these insulin dependent cells are vesicles that are holding transporters, specifically glut transporters. And what this second messenger does is it causes exocytosis of this glut transporter to the cell membrane. And now we have this glut transporter. Remember, a glut is a glucose transporter on the surface, on the cell membrane. And that's where we want it because we need it there so that we can move glucose down its concentration gradient into the cell. And now the cell is able to use glucose as a resource. So what happens in a cell, like a liver cell, that is not dependent on insulin? Well, they also have insulin receptors. So here is another insulin receptor. What makes them different, however, is that their glut transporters are not found in vesicles within the cell. Their glut transporters are always on the surface. Say they're always here. So insulin will come and bind to its receptor, and glucose will move down its concentration gradient. So now glucose is in the cell, but as insulin binds to its receptor, it causes a chemical reaction in glucose that makes glucose turn into what's called glucose 6-phosphate. And since we're a liver cell, this glucose 6-phosphate becomes glycogen. And remember, glucose, carbohydrate short-term storage, especially in the liver, is glycogen. Okay, so the liver stores glucose as glycogen. One thing I forgot to mention is that as concentrations of glucose go down in the blood, these insulin-dependent cells will then pull these glut transporters back in until, again, we eat another meal, concentrations of glucose go back up, and insulin will bind to its receptor, have another second messenger cascade, and then exocytose the glut transporter back to the surface. Okay, so that's the mechanism of insulin in the blood. So we've talked about beta cells that make insulin, but the pancreas also has endocrine cells called alpha cells, found in these islets of Langerhans or pancreatic islets. Well, these alpha cells, they do not make insulin, they make what's called glucagon. a hormone called glucagon. And it's produced when glucose levels, when concentrations of glucose are low. Not high, but low. Its target is the liver, so it acts on the liver. Glucagon acts on the liver, and it causes a breakdown of glycogen. Now remember, glycogen is how the liver stores glucose. So its aim is to increase the level of glucose in the blood. Now let's talk about cellular respiration. And this is really the beginning of what you need to know for chapter 3. In your notes, there are some things like the law of thermodynamics that I will ask you to know for the exam, and also the definitions for metabolism, catabolism, and anabolism. But those are available in your notes that go along with this video for chapter 3. Alright, so what I want you to know from chapter 3 for me is cellular respiration. So let's begin with this equation, C6H12O6. We know that is glucose. When we add in oxygen, we form water, CO2, and our energy molecule, ATP. So where does this really occur? Well, we need an organelle called the mitochondria, often referred to as the powerhouse of the cell. It's important we know the anatomy of the mitochondria, the matrix, the outer membrane, the inner membrane space, and then the inner membrane. And this is the section really that we're going to be looking at. Right outside the mitochondria, the matrix, and within the inner membrane space. This is where cellular respiration happens. So let's get some of these definitions out of the way. So I mentioned electron carriers before. We had NAD plus, and FAD. And they become electron carriers when we add in electrons. And when we do that, they become NADH and FADH2. So now they're cofactors, or high energy molecules, and they can basically be cashed in. These electrons can basically be cashed in for ATP, which is what we want. So what is ATP? ATP is adenosine triphosphate, meaning it has 3 phosphate molecules attached to an adenosine. And the energy is held within the bonds of the phosphate, the most being within the last one. So to form ATP, we have to have an ADP, adenosine diphosphate. That's an adenosine attached to 2 phosphates. This last phosphate that we need to get attached to this ADP is actually held or bonded to a water molecule. It's tightly held to a water molecule. And the strong bond between the water molecule, once we break that, will release a lot of energy. So how do we get the energy to break this bond here so that we can form ATP? Well, we get it from glucose through cellular respiration. So the first part of cellular respiration is glycolysis. And glycolysis happens outside of the mitochondria in the cytoplasm. So make sure you know where each part actually happens. So let's begin with a molecule of glucose, C6H12O6. So as it goes through glycolysis, we end up forming two pyruvate. From one molecule of glucose. The energy we formed we've made two electron carriers and two ATPs. So really not a whole lot of energy yet. There's an intermediate stage that goes from the pyruvate to the acetyl-CoA. I spelled that wrong. And we end up making one of the byproducts of cellular respiration, CO2. And two more electron carriers. Still not a whole lot of energy. The next portion is the citric acid cycle, or the Krebs cycle. Either name. Krebs with a K. The Krebs cycle, or the citric acid cycle, doesn't happen in the cytoplasm. It happens within the mitochondrial matrix. So it happens within the matrix of the mitochondria. Okay. So this acetyl-CoA goes through some enzymatic reactions, removing of carbons, and we end up making some electron carriers, 8 of them. Remember, these are high energy molecules. We make 2 ATPs. And some more CO2. Because remember, this is a respiration, so of course, if we utilize oxygen, one of the byproducts is going to be CO2. Alright, still we have not made a whole lot of energy. So where does all of this energy from glucose come from? Well, we still have one part of cellular respiration left to talk about, and that's the electron transport chain. So let's gather all of our electron carriers and send them down the electron transport chain. So how many do we have? We have 2, 2, and 8. So we have 12 electron carriers. So this happens along the inner membrane. This is the matrix of the mitochondria. And this is the cytoplasm of the cell. So you have proteins found on the inner membrane of the mitochondria that are going to utilize these electrons and turn them into ATP. So what happens first? So let's get our electrons. Remember, we had 12 of them, and they're going to be handed off down these proteins. Protons, or hydrogen ions, are pumped into the space down their concentration gradient. So they're moving down their concentration gradient. And these electrons are again then handed off downhill. So what I mean by that is that they're losing energy as they move down these proteins. So here they were higher energy than they are here. So we're losing energy. As they move down, we continue to pump in more protons into this inner membrane space. So we're collecting protons in here. And we continue to pass off electrons down these special proteins. We continue to pump in protons down its concentration gradient until we have a higher concentration of protons, and they want to get out. They want to get back out. So when these protons want to get back out, we have this specialized protein called ATP synthase. And this ATP synthase will spin. This ATP synthase will spin, and it works like a water wheel, pushing these protons out. Back out. So let's draw it like a water wheel. Like you would see in a water mill. Flowing, pushing water, the wheel being turned like if it was placed on a river. So here are our protons. Being pumped out. And every time a proton passes through this ATP synthase, it takes an ADP and a phosphate, and it turns it into an ATP. And remember what this extra phosphate was bonded to? Remember, it was stuck to a water. Okay? So who is going to be the final electron acceptor? So who's going to be this final electron acceptor? It actually is oxygen. Oxygen is the final electron acceptor, and you make ATP. Okay? So here is our oxygen and the electrons from the hydrogen ions bonded to, and what I want you to know is that oxygen is the final electron acceptor for you to make ATP. So know at least number 5 here, and what protein makes you do this? It's ATP synthase in the electron transport chain. Now let's add all of this all up. Remember these electron cars, these electron carriers? I said we cache them in for ATP in the electron transport chain. One NADH comes to about 2.5 ATPs. And FADH comes to around 1.5 ATP. That means we can make roughly 26 to 28 ATPs in the electron transport chain. So if we add all of this up, in glycolysis we made 2 ATPs. In the citric acid cycle we only made 2 ATPs. And then in electron transport chain we'll say we made 28 ATPs. That means in total we can make 32 ATPs from just one glucose molecule. Okay, so make sure that you know these numbers. Okay. The last thing that I want to mention is some variations. If we go back to this slide right here, is where does the energy come from? What if we didn't have a glucose molecule and say instead we had a protein? We had a protein molecule. Remember, proteins are polymers of amino acids. Well, if instead we had a protein, it would be exchanged here for pyruvate, and it would continue on down this way. What if instead we had a fat or a lipid? And remember, a lipid is a fatty acid and a glycerol. Well, the fatty acid would be exchanged here for acetyl-CoA. The glycerol would actually be exchanged for glucose itself. So make sure that you know these variations in cellular respiration. Proteins for pyruvate, fatty acids for acetyl-CoA, and glycerol for glucose itself. Okay, that's it. That's it for chapter 27 and chapter 3. Happy studying.